All right, so we're going to start Chapter 7, which of course is about our planet. The thing about this that's important is, as we go through the solar system, we're going to compare the other planets, when we can, to the Earth. So, knowing some properties of our planet, which of course we know the best, is always comparing the properties that we know about to other planets. It becomes very, very useful. All right, so this is the things that we're going to talk about: the structure, the atmosphere, greenhouse gases, the interior of the Earth, a little bit about the age of the Earth using radioactive decay, some surface activity, the volcanic activity, earthquakes, things like that. The magnetosphere, which goes, that surrounds the Earth, is caused by the core of the Earth, the iron nickel core of the Earth moving at a different rate than the surface, and of course the tides. All right, so this is so let's just jump into this. The overall structure of the Earth. Of course, we have the crust, and it's showing that it does vary in thickness, anywhere from as thin as 5 kilometers thick to 50 kilometers. And then below that we have the mantle. The mantle is, that's like where the lava comes from when there's volcanic activity. It's not a liquid per se. It's kind of like it's a hot plastic, if you will. It can move around, but it's still considered a solid. All right, and then we get to the outer core, this reddish area here, and the outer core is actually liquid, and it is made mostly of iron and nickel, and I'll explain how we know that. And then there's the interior core, which is solid. It's so dense there that it's actually solid material. The distance from the center of the planet to the surface is roughly, varies a little bit, but roughly 6,400 kilometers. All right, so that's important to know. All right. Of course, the hydrosphere is the oceans. The atmosphere is just above that, and then the magnetosphere, which really starts here in the core, goes way out into space. All right, so we'll talk about that a little bit. All right, so looking at the atmosphere, so this is actually showing how the temperature changes with height, and so you can see that the temperature goes down once you get above the stratosphere. It basically starts to go down. And let's see what else. Yeah, I guess that's about it. And then of course it says that the troposphere. This is the part basically from the surface of the Earth to the tops of the clouds. This is basically where all the weather takes place. Everything pretty much that we experience takes place in the troposphere. The stratosphere, of course, is where the ozone layer is, and then above that is basically space is roughly, I don't know, it depends on who you talk to, but roughly about 100 miles or so above the surface of the Earth. You can truly, you can actually be considered to be in space. But before that, the atmosphere is so thin that for all intents and purposes, you're in space. Okay. Some people talk about going to, like, if you look at some of the spacecraft that are being launched, or these private companies that are launching spacecraft, they're talking about being being 50 miles above the Earth, and they consider that in space. So, it depends on really who you talk to. All right, so what happens with the Earth's atmosphere? The sunlight hits the ground all over the planet, and it warms the ground, and then, of course, you have, the air in the higher parts of the atmosphere come down and basically cool off. And then, the hot air rises, as you probably have heard before. Hot air rises, the cool air falls down, and that whole process is called convection. It's when the hot air molecules physically move from place to place. So the ionosphere is a region, well above the stratosphere, where basically the sun's light will cause the air molecules to ionize. That just basically means they lose electrons. They're not neutral molecules anymore. And actually, that particular area reflects AM radio, and it'll actually bounce several times off of the ionosphere. Depends on exactly how charged up the ionosphere is. But there have been cases where people could use ham radio, which is roughly in the AM range, and bounce a signal off the ionosphere several times, and let's say reach Australia all the way from the United States. That's unusual, but it has happened. Okay, so the ozone layer is between the ionosphere and the mesosphere, and this, of course, is the area. Ozone is basically O3 molecules, 3 oxygen molecules bonded together in a molecular bond. Anyhow, that is important to us because it absorbs most of the ultraviolet radiation, not all of it, but most of it. And ultraviolet radiation is very harmful to life. All right, and these CFCs, these chlorofluorocarbons, were actually used a lot more frequently back in the 1970s, and what we found is this particular chemical compound caused holes in the atmosphere, in the ozone layer. And of course this is extremely dangerous, and a lot of these this particular product has been banned. When I was a kid, this was a very popular product that was found in like hairspray, for example, when hairspray was very popular a long time ago. All right, So of course, we just talked about that the surface is heated by the sun. Of course, that's pretty obvious. And of course, the sunlight gets absorbed by the Earth. It warms up the Earth, and during that process of warming the surface of the Earth, and of course, it does this to the oceans as well. What happens is that energy, that thermal energy, gets re-radiated in the form of infrared. So that's below the visible spectrum. We usually associate with infrared with heat, thermal energy. Anyhow, what happens, of course, this is the whole idea of the greenhouse effect, is there are certain molecules that will absorb that infrared radiation, and the biggest culprit of these so-called greenhouse gases is water vapor. Actually, it's actually much more effective than carbon dioxide. All right, so why are people so concerned about the greenhouse gases? Well, see, the thing is, the water vapor will, of course, has this natural cycle where the water vapor comes out of the atmosphere through, of course, rain or some kind of precipitation, snow or something like that. Whereas the carbon dioxide does not. It doesn't naturally. Well, I'm sorry. Let me back up a little bit. It does. A little bit of it does come out of the atmosphere naturally. For example, plant life uses carbon dioxide. But the human beings, of course, have been putting so much carbon dioxide into the atmosphere that if you were to actually watch since the like the 1950s when we started recording this, the curve is it's not even a straight line up. It's an exponentially increasing curve, which is pretty alarming. That is the amount of carbon dioxide caused by humans. All right, so so this is always an interesting question. People ask this all the time. Especially little kids will ask their parents, why is the sky blue? A lot of people will talk about, it has to do with the oceans or reflection of the light. It has nothing to do with that. Okay, so here's the reason that light, that the sky is generally blue. So you have all the colors of the rainbow coming in to the atmosphere, of course, from the sun. And what happens is because of the contents of the atmosphere, which is mostly nitrogen and nitrogen molecules, N2, two nitrogens bonded together. Anyhow, what happens is because of this, the size of those molecules, the blue light tends to bounce around more frequently than any of the other colors. And so the blue light bouncing around causes the background of the sky to appear blue. And that's really what is causing the sky to be blue. Okay, nothing to do with the oceans or anything like that. All right. So this scattering is proportional to 1 over the 4th power of the wavelength of light. That's called Rayleigh scattering. Anyhow, that's all right. So notice, of course, when the sun is closer to the horizon, you're not getting blue. You're getting more oranges and reds. And the reason for that is the molecules close to the horizon, just because of gravity, are larger. They're physically larger, and so you're seeing some of the the longer wavelengths, the reds, the orange. Well, I should start with oranges and reds. All right, so that's why the sunrise and the sunset are generally not blue. All right, so what about the Earth's atmosphere? The original atmosphere of the Earth was actually a lot more simple than it is today. We think that originally there was a lot of hydrogen and helium, which of course that stuff escaped from the Earth, and then as volcanic activity increased, we get more and more nitrogen. There's actually some ammonia and some methane as well. But what happened more than 3 billion years ago, life, very simple life, microbial life, occurred on the Earth, and that changed the atmosphere. It turned, through photosynthesis, the atmosphere went from, being this very early atmosphere to having an oxygen-rich atmosphere. Now, oxygen-rich means, about 21% of the atmosphere is the O2 molecule, the thing that we breathe, right? The two oxygens bonded together in a chemical bond. All right, so this is here's the nice exponential curve that I was actually talking about earlier. And notice, since the Industrial Revolution, this has gone up, not at all in a straight line. It's actually an exponential growth. and it keeps going up. We really do need to do something about this. I mean, a lot of people are talking about this around the world. All right, I'll talk to you in the next film.